Everybody, thanks for coming. I'm going to give it just a few more minutes and then we'll get started.
Yeah. Can you still see my screen?
Yes.
Okay, because I lost the control of how to change the slide. Oh, sorry. No, it was working great.
Take your time.
Oops. I think it's a Zoom window. Okay, let me just quit and join again very quickly.
Okay, that's fine.
You have to allow me again to share the screen. Okay.
Is that good now?
Yeah, well, I still have the toolbar, but it will be fine. I don't see my full screen, but I think that will be fine.
I think there's a drop down on the toolbar. If you go to the dots, then you can hide it if you would like.
But it's not the Zoom toolbar that I see. It's like my computer toolbar.
Oh, okay. Then I don't know. We don't see that.
Okay. Yeah. Well, that we're going to do with it.
Yeah, are you ready to get started then?
Yeah.
Okay, great. Oh, well, thank you for coming, everybody. Our speaker today will be Audrey Delpech from UCLA, and she will be talking about internal wave interactions with eddies in the atmosphere from a high-resolution regional simulation of the California current system. So thank you very much, Audrey, and thank you all for joining us today.
Yeah, well, thanks for inviting me. Hello again, everyone. So yes, as Maura said, I'm a postdoc at UCLA. I'm working with Roy Barkan and Jim McWilliams, and also other collaborators from different institutes. My postdoc research focuses on the internal wave dynamics and more specifically on their interaction with eddies and with the atmosphere. And despite what I have advertised for the talk for today, I'm not going to talk in the end of the interaction with eddies, and I will only focus on the interaction with the atmosphere and with the wind. So just to give a little bit of context, so why do we study internal waves? One main motivation is for the global ocean energy budgets. So we know that internal waves constitute a large reservoir for the energy in the ocean. They have a strong potential for dissipation, and it's thought that most of the diapedal mixing in the ocean is coming from the breaking of internal waves. So better knowledge of their generation, propagation, and life cycle will give some better insight, or is required to better understand and quantify the global energy budgets. A second point is that understanding internal waves is very important for the interpretation of SWAT satellite altimeters, such as the SWAT satellite that will be launched very soon, and that will measure ocean topography at very small scales. And at those small scales, the ocean topography is a combination of geostrophic currents, eddies, but also an aliasing of internal waves, because the satellite won't have a very high frequency. We focused our study in the California current system, which is an interesting region because it has a very quite strong meso and sub-mesoscale dynamic, which is seasonally driven by the development of the upwelling along the coast due to the winds blowing southwards. It's also a generation hotspot for the internal waves, more specifically for the internal tides, due to the presence of the Mendocino Ridge that you can see on this map. And here, so on this map, you can see the amplitude of the M2 internal tide, which is obtained from a combination of different satellite altimeters. And you can see that there is a beam, or there are beams of energy radiating away from this Mendocino Ridge, southward and northward. In this region, there is also a substantial amount of the internal tide, which is coming, which was remotely generated, and which are propagating into the domain from the Hawaiian Ridge. And finally, it's a region where we also have two ongoing in-situ observation program, which is the SWAT Calva, which will take place at the intersection of the two SWAT tracks here, and the SMOD, the Submesoscale Ocean Dynamic Experiments, which takes place in the region offshore of San Francisco. And this two observation program will likely provide some observation to compare with our models. So the main question I've been focusing on for this internal wave atmospheric interaction part is to better understand the Earth-sea interaction at high frequencies, and especially at the periods of the internal waves, and if there is wind and current interaction at those frequencies, and how this interaction might or might not affect the energetics of internal waves. And so first thing we can look at when, first just to give you an idea of the simulation we're using. So we're using generally a nested simulation that we nest down while increasing the resolution. So here we started to force the internal wave or the high frequency at a 4-kilometer simulation, which is forced at the boundaries with a low frequency simulation, a coarser simulation from the ROMS model, and the high frequency from the global HICOM model, and which is forced at the surface with the Worf-Harley atmospheric forcing simulation run with the Worf model. And for this from this 4-kilometer simulation, we nest down to 2 kilometers and 600 meters. And the results I'm going to talk about today focuses on the 2-kilometer simulation. And so the first thing we can look at when we talk about current and wind interaction is to look at the co-spectrum of winds and surface currents. And so here, this is what I'm showing for the 2-kilometer simulation as a function of wave numbers and frequencies. And the way to interpret this figure is that when the co-spectrum is positive, it means that there is a net input of energy from the wind to the ocean. And when it's negative, there is a depletion of energy from the ocean toward the wind. And so what we can see on this figure, and that we already knew, is that at large scales, there is a net input of energy from the wind to the ocean. That in the meso and submesoscale range that we can see here, there is a removal of energy, which corresponds to a phenomenon called generally the educating effect, and which was described in papers such as the one by Lionel Renaud in 2016. And which is perhaps less known is that at higher frequencies, there is also a depletion of energy, especially in the near inertial band here at the 12-hour period, which corresponds to the M2 period, and along the dispersion relation for the main internal waves. And so similarly to the educating effect, I call this the internal wave killing effect. And you can see already from this plot that the order of magnitude here of the wind work, of the negative wind work at high frequencies is very close to the one in the meso and submesoscale range. But to better quantify the energy sink associated with this internal wave killing effect, I computed the wind work in the physical space. So by taking the average of U prime tau prime of the scalar product between these two quantities. And here the prime is a filter that specifically targets this region of the spectrum. So it retains a spatial scale smaller than 180 kilometers, which will likely retain all the scales associated with the different baroclinic modes, and a temporal filtering, which is a bandpass between 4 and 14 hours, and which target the internal tides more specifically. So in the rest of this talk, I'm going to leave aside the near inertial waves, which is a bit of a different story. And you can see that at those scales, so the wind work is mostly negative and is intensified in the region here close to the Mendocino Ridge in the eastern part and in the western part. And on average over the domain, there is a net removal of 0.07 gigawatts of gigawatts. So that's the value integrated over the domain. And to get a better sense of the order of magnitude, we can compare this with the total production of internal tides in these scales, which is given by the barotropic to baroclinic conversion, the W prime B prime, or prime being here the same filter. You can see that this conversion occurs mostly close to the Mendocino Ridge and along the continental shelf. And there is a total amount of 0.5 gigawatts. And so the ratio between those two numbers is 10%. So we can say that there is 10% of the energy which is converted from barotropic to baroclinic motion that is dissipated due to the wind work. So it's not negligible. And if we further decompose this contribution, this wind work between the barotropic and baroclinic contribution, we can actually see, so here it's the barotropic and baroclinic contribution, but on purpose on the same scale. We can see that almost or 100% of this negative wind work is actually due to a baroclinic contribution. And this makes sense if we look at the distribution or the repartition of the total surface kinetic energy between barotropic and baroclinic contribution. You can see that the total KE or surface KE is actually mostly contribution from baroclinic currents, the barotropic currents being much more weaker in the open ocean. So the question now is, what is the mechanism behind the internal wave energy sink associated with this negative wind work? And similarly to the eddy killing effect, I have interpreted this negative wind work as a result of the current feedback. And so the current feedback is a parametrization, which is generally used in ocean models. And that is just a way to take into account that the imprint that the surface currents might have on the winds in the formulation of the wind stress. And so just to give you an idea of the fact that the current feedback is involved in this negative wind work, I rerun the exact same simulation without the current feedback parametrization. And here is how the co-spectrum of the winds and surface currents looks like. And you can see that most of the energy sink at high frequencies and also at meso and submeso scale disappear in the simulation. So to understand why the current feedbacks create an energy sink, we can come back to the schematic proposed by Lionel Renaud in his paper in 2016. So I'm showing it here first for the eddies, and we'll see that it works in the similar way for the internal waves. So the idea is that if we have an eddy like this with a wind or a uniform wind blowing on top of this eddy, so here it's southward, this will create an asymmetry in the wind work. On the side of the eddy where the wind is against the currents, the stress will be larger due to this definition, and this will create a large negative wind work. And to the contrary, on the side of the eddy where the wind is aligned with the currents, the wind stress will be smaller, and this will create a small positive wind work. So on average, on the eddy, this will result in a negative wind work. And now if we take an idealized case for an internal wave or any periodic signal, and so that we have, like, during the first half of the period, a current flowing southward, and during the second half of the period flowing northward, on top of, let's say, southward wind. Then we will have, during this first half period, a small wind stress that will result in a small positive wind work. And during the second half of the period, a large wind stress that will result in a large negative wind work. So if we average in time, we will have a negative wind work as well. Now, the main difference between the two configurations here is that the eddies are isotropic. So whatever the wind direction is, we will always be able to do this same schematic. But the internal waves are polarized, and especially at high frequency. So we can see that it will, like the relative angle between the wind and the currents will matter. And so the question I'm trying to understand is if the winds can modulate the internal wave killing effect and the associated energy sink, because we know that the winds is so quite variables. So to answer this question, I have first focused on the variability of the, I have first looked at the variability of the internal wave. And so here I'm going to show you the example for the baroclinic M2 internal tide. And a way to look at the variability of this internal tide is to demodulate, to do a complex demodulation of the signal associated with the baroclinic motion. And so this demodulation will give us an amplitude, a phase, and a residual. And if we look at the time series over 1 year of the simulation of this amplitude, we can see that it exhibits some low frequency variability, and in particular, a nice seasonal cycle. So here it's generic. I'm showing it for the baroclinic mode 1, but actually it was done for mode 1, 2, and 3, and it looks very similar for all of these modes. If we look at a spectrum of this time series, we can see that there are actually two main frequencies that stand out, which are the 14 and 5 days frequency, which corresponds to the spring and neap tide cycle, and it's also present in the barotropic signal, and also a lower frequency, which corresponds to the seasonal cycle. And so I wanted to see if this seasonal cycle or part of this seasonal cycle is wind driven. And by wind driven, I mean like driven by the driven by the modulation of the negative wind work associated with the current feedback. So a way to look at this is to look at the time series of the amplitude of this internal tide. And here I'm showing the example of the M2 for now, but we're going to look at the different modes a bit later. So we can look at the amplitude, at the variability of this amplitude of mode 2 and 2 internal tides in the simulation with and without the current feedback. So the first thing that you can see is that in the simulation without the current feedback, the amplitude is larger because the energy sink associated with the current feedback is not active. And we can also see that this seasonal cycle actually already exists in the simulation without current feedback. So it's not, the seasonal cycle in itself is not driven by the modulation of the negative wind work. However, you can see that the difference between the amplitude without and with current feedback is different. For example, here, the difference is smaller than here. And indeed, if we look at the relative difference of these two amplitudes, so which corresponds to the percentage of reduction due to the current feedback, we can see that there is also a seasonal cycle of this percentage of reduction. And so I have tried to relate the seasonal cycle. So here we can see it's, for example, stronger in the late spring, early summer. And I have tried to relate this seasonal cycle of the percentage of reduction to the winds and the current magnitudes. So it seems that this this seasonal cycle, and in particular this event where the reduction is smaller, corresponds, or is in phase with the amplitude of the internal tide themselves. So the reduction seems to be larger in the during the time of the year where the amplitude of the internal wave is larger. So which makes sense because the wind work is also proportional to the currents. There is no clear evidence that this time series can be related to the wind variability. at least from the wind amplitude. The winds has a seasonal cycle over the domain, but it's also spatially variable. And here I'm showing a diagnostic which is integrated over the domain. So for now, there is no clear relation, but this necessitates more investigation. And finally, the last point I wanted to talk about is the variability of the energy sink across the different baroclinic modes. So I have shown you the percentage of reduction associated with the current feedback for the mode 2, but we can also look for the mode 1 and 3. And you can see that the percentage of reduction of the internal wave amplitude due to the current feedback increases as we increase the baroclinic mode. There is an average of 3% of reduction in the baroclinic mode 1, an average of 10% of reduction in the baroclinic mode 2, and 12%, almost 12% of reduction in the baroclinic mode 3. So it seems that higher modes lose more energy due to the current feedback on internal waves. And an explanation we came up with to justify this is to look at the polarization of each mode and their main direction with respect to the wind directions. So we know that the wind has a preferential direction. So here we're looking at the wind rose. It shows on the radial axis the density of probability of the wind blowing in a particular direction, and in color the wind speed or the average speed associated with that particular direction. So from this plot, which corresponds to which takes into account the full year time series of the wind, you can see that the wind has a preferential direction, and is mostly blowing in the south-southwest direction. Now, if we look at this same kind of plot, but for the baroclinic mode 1, and sorry, I haven't precised here, but this is still the M2 internal tide we're looking at. So it's a current associated with mode 1 M2 internal tides. We can see that there is, the mode 1 is slightly polarized, but in the east-west direction. So here, you can see that the stronger currents occur in this east-west direction. And that's very different from mode 2 and 3, which are slightly more polarized, and whose polarity is aligned with almost the north-south direction for mode 2, and a direction very similar to the one of the wind direction for the mode 3. And this will actually impact the efficiency of the energy sink associated with wind work. Because if we come back to this wind work definition, which is the stressed scalar product with surface currents, so this part is constant, but if we plot the magnitude of this part as a function of the relative angle between the winds and the currents, and this is what I have done here. So here on this polar plot, the angle that you see here now is the relative angle between the winds and the currents. You can see that this term is almost twice as important in this direction when the winds are aligned with the currents than it is when the winds are at right angle with the currents. So the wind work will be twice more efficient when the winds are aligned with the currents. And this can explain why the mode 1 loses less energy due to the wind work, because it's polarized with velocities which are mostly at right angle with the winds, compared to mode 2 and 3, which have velocities more aligned with the winds. And yes, if we ask why is mode 1 polarized in that east-west direction, and mode 2 and 3 are polarized in the other direction. So what we were thinking of is to look at to come back to this surface kinetic energy map of mode 2 and 3, And here we can see that mod 2 and 3 are mostly actually locally generated at the Mendocino Ridge and will propagate north and southward from this ridge, which will so generate north and southward velocities. While the mod 1 is not only locally generated at the Mendocino Ridge, but also remotely generated and propagates from the Hawaiian Ridge towards or inside this domain and propagate eastward through the open boundary conditions. And that this signal likely dominates and will result in an east-west polarization. Yes, and so just to sum up what I've just shown you, so what did we learn about the wind internal waves interactions? It's first that the internal waves are associated with current feedback on winds that generates a negative wind work, inducing a net energy sink for the internal waves. We quantified this energy sink for the internal tides, and we estimated that it corresponds to approximately 10% of the production of energy from the barotropic to baroclinic conversion. We've also seen that this the magnitude of this energy sink has some variability. It has a seasonal variability. It is in particular stronger during the spring. But for now, there is no clear evidence of the mechanism behind this temporal variability. It's likely due to a combination of the internal tide amplitude itself and a wind seasonal cycle, but this still needs to be refined. And there is also a modal variability because we've seen that higher mods such as mod 2 and 3 lose more energy than mod 1 due to this negative wind work. And this can be explained by the local configuration of the internal wave or internal tide polarization and the wind directions. And we've seen that the winds is more efficient at extracting energy from the internal waves when it's aligned with the currents. And this was the case. So this was the case for our configuration of the California current system, but this might be different in other regions where the winds and the internal waves might propagate in different directions. So the ongoing work consists in better understanding the seasonal variability of the magnitude of the energy sink, and some nice perspectives of this work will be to assess the wind work on these internal waves in different regions, or even if possible at a global scales from models, but also if possible from observations. And from this, for this, we're going to need concomitant measurements of winds and surface currents. And I think I will leave it to questions from now.
Great, thank you very much, Audrey. That was a fantastic talk, and I think provides a lot of space for us to have discussions and for future work. So let's start by giving Audrey a round of applause virtually. And then I'd be happy to take any questions. So you can either raise your virtual hand in Zoom or just write a note in the chat if you'd like to ask a question. Yeah, and I'll start off. Yeah, so I was wondering, do you think that the wind has a role in shaping the polarization of the tide? It seems like the configuration of the Mendocino Ridge is really important here in this region, but does the wind have any, since it is an energy sink, does it have a role in shaping the direction of the tide and shaping the spatial distance away from the ridge that these the baroclinic modes can propagate?
Yeah, that's a good question. I haven't investigated very closely, but I think it will definitely shape the ability of the tide to propagate away from the ridge. So if there is more damping that we've seen, for example, from mod 3, it will likely propagate less less propagate from this Mendocino Ridge. If it can shape the polarity, I don't know about that. Yeah, I don't know. yeah, it might play a role if it damps beams that are propagating in a certain direction and not in another direction. But so probably on average, yes. Locally, I don't know.
Yeah, great, thank you. Are there any other questions? Go ahead, Tom.
Hi, Martin. Could I ask a question?
Yeah, let's do Tony and then Tom.
Oh, okay. Sorry for cutting ahead of Tom. So I have a question about the last point on this slide. To do that analysis observationally, is there a requirement on the sampling, temporal sampling of the simultaneous measurements of wind and currents?
Yes, so yes, that's right. So to compute this all this quantity, so the output frequency of my simulation was 1 hour. So it's quite high resolution sampling. I guess this won't be possible with satellite measurement, for example. But maybe there is a way to like do something more statistical and not need this 1 hour frequency sampling. But yeah, for now, 1 hour would be my answer.
Okay, thank you.
Audrey, I was wondering about what this would imply for vertical shear in the upper ocean. You know, I imagine going along with this wind work would be some kind of heightened vertical shear in the internal wave bands.
Yeah.
And does your model, you know, resolve everything that's needed in the upper ocean to do this realistically?
Yeah, I haven't looked at the vertical shear at all. I don't know how this might impact the vertical shear. I honestly don't know. I think, yeah, I really focused on the surface velocities, but that's, yeah, that's a good question.
Well, the reason I asked is I've looked at spectra of vertical shear in the upper ocean, and I was expecting to see low vertical shear for the tidal frequencies, but it was in fact one of the highest, or you know, there was more vertical shear at tidal frequencies than others.
Okay, so that means higher mods, higher proclinic mods in this at those frequencies?
No, just near the surface, as if the atmosphere is acting as a drag on the ocean at those frequencies.
Okay, okay, that's interesting. Yeah. Okay. So yeah, that might be a reason.
Great. Are there any other questions here? Yeah, Jacob.
Audrey, really nice talk. So I'm curious, so Lionel, for the eddies has shown that the change in the stress divergence on the atmospheric side matters for the wind speed, so partially compensating the current feedback. Are you seeing that, or is the time scale fast enough that it doesn't matter for these?
So you mean that in a fully coupled simulation that this might sorry, I'm trying to better understand the question. So you mean
perhaps I missed it. Are you running with the sort of built-in parameterization, not in a coupled?
Yeah, exactly. I'm running it in with the current feedback parameterization, but not in a fully coupled simulation. And yeah, I think that's going to be one of the perspectives as well, to see if like a fully coupled simulation, how it affects this magnitude of the energy sink. Yeah, because that's true that for the eddies, the magnitude was reduced when looking at the fully coupled simulation.
Great, thank you. Nice talk.
Thank you.
Can I just add something?
Yeah, go ahead.
Yes,
And before you do that, I want to say that there's a note in the chat, and also in response to Jacob's question.
Yeah,
Brian.
so I'm one of Audrey's collaborators on this, and I was just going to note that Audrey's also using these simulations to, I think, make some fundamental understandings of the cause of the internal wave spectrum. So, you know, Roy Barkan suggested that eddies also might have something to do with the generation of the spectrum. So by contrasting simulations with and with, you know, where you have only waves versus waves plus eddies, I think Audrey will make some progress on that. I hope you don't mind my saying that, Audrey, but I just wanted to mention that she's kind of doing two projects and you only heard one of them today.
Yeah.
Yeah.
Yeah, in the end, I didn't talk about the edgy internal wave at all, interactions at all. I thought it would be enough for one talk.
Yeah, hopefully we'll get a chance to hear that talk as well. I guess I had a question about as you extend this work to other regions, what do you think will be the key characteristics of those regions that might make this effect more or less important?
Yeah, I think it can be. So I think it can be really region dependent, because it's going to depend on the wind directions and on the main direction of propagation of the main tidal beams. So yes, it's like really up to the wind regimes and the local configuration of the topography and the generation sites. So I think it's really worth it, like, to extend it at different regions or a global scale. Yeah. But yeah, and it's also not the region where we have like, I mean, the Mendocino Ridge is a strong generator, but it's not like as strong as the Hawaiian Ridge or as the Luzon Strait, for example, in the Pacific. So might be even more important in terms of magnitude in regions where the internal tides are even more important.
Mm-hmm. Okay. The last call for any questions. Yeah, then let's thank Audrey again for this talk. And there will be a talk next week. Luke and I will be talking at the same place and the same time. So we'll look forward to seeing you then.
Thank you very much.
Thank you. Bye-bye.
Thanks, Audrey.
Bye.